Hey, Assalamualaikum warahmatullahi wabarakatuh. Welcome again to my lab reservoir channel. Good afternoon, good evening, good morning, wherever you are. So today's occasions, over the next 30 minutes, I would like to talk about kind of introduction concept of perched water context, refer the phenomenon of water entrapment behind barrier during the migration of hydrocarbon in reservoir. Actually, these phenomenon leads to locally elevated free water level or hydrocarbon water contact position. And I put on the title fundamental control of perched water contact as a review. And it is shown that rock quality and relative permeability play a significant role in the formation. Building realistic and reliable subsurface model requires a detailed understanding of both rock and fluids involved. In addition, estimating hydrocarbon volume factors such as permeability, saturation height model, free water level, and hydraulic communication play significant role in determining recoverable reserve. And I believe understanding this phenomena is very crucial as they may impact the distribution of hydrocarbon volume and overall the recovery factors. So let's start. A brief introduction, continuous understanding of perching, a phenomenon not previously explored. Through simulation, it's demonstrated how water permeability at the top of barrier play a crucial role in enabling perching. The saturation and entry pressure, along with the capillary pressure shape factors, which are important parameters that determines the thickness of the transition zone and the height above free water level where the water becomes immobile. Additionally, the reference published study reveals that perchings affect rock with lower permeability to a lesser extent compared to the rock with higher permeability, highlighting the distinction between capillary pressure and the buoyancy. Um, the next figures on the following slide show a cartoon representation of possible scenario where perched water contact is exercised through formation pressure. The formation pressure and the example of free water level are depicted for the main field first free water level and the perched zone of second free water level were indicating a difference of approximately, I think, somewhere 350 feet. And this information adapted from the study Johnson et al. In 86 helps in understanding the concept of perched water contact and the impact on hydrocarbon reservoir. Perched water contact explained as a situation where water accumulates and form a separate zone above the hydrocarbon column in oil and gas reservoir. This can create confusion, hinder hydraulic communication across the field. As an example, such as a perch contact is observed, I think I use a Fulmer field in the central North Sea, where significant difference in the free water level between different part region of the field was exercised, identified, impacting the understanding of hydrocarbon distribution. In general, perching is expected to be more pronounced in lower quality rock formation. A field background, a Fulmer structure is relatively simple dome shape anticline with prominently dipping flanks, 8 to 25 degrees. One main oil water contact regions, 10,840 subsea. Is represented well number 2 and more localized, while the higher oil water contacts Going further in the northern flanks is around 10,560 subsea, well number 2. The western flank of the field is conformable, capped by the Kimmeridge clay formation, while the eastern flank is conformable, overlaying by the chalk, overlaying the regional extensive late Kimmerian unconformity. The field is cut by a northwest southeast trending normal fault, mainly head eastward, but subsidiarily westward shading antithetical fault are also present. The structural configuration is interpreted as reflecting late Jurassic salt withdrawal from below Upper Jurassic secondary rims incline, which result in the characteristic of pot-shaped geometry. The fault is related to the Outhorse central graben boundary fault system occurred prior to the formation of the late Cimmerian, early Cretaceous unconformity surface. I think that's kind of field background of an example. The next provided figures show a comparison of log-derived saturation with height above free water level in two different wells in the grain field. Well number 2 correspond to the Perched zone, and based on this observation, expect the transition zone above the Perched zone is to be compressed. The data is fitted by considering change in rock quality between these two wells. But the challenging aspect is to explain how to explain is sudden change in water saturation in well 1 under 5 meters above height above free water level, which could indicate deviation from the primary drainage such as imbibition. The phenomenon of water trappings against a fault highlights the lack of understanding regarding the microscopic parameters that control the process. It also raises the question of how rock permeability influence water perching and whether the effect is intensified or diminished with change in rock quality. The trapping of water against a fault and highlight the lack of focus on understanding the microscopic control the process. And it's also mentioned the grain field in Norway as an example of another mechanism of oil trapping, suggested that the transition zone could be compressed. The common factor in this case, high quality rock, which affect the predictability of the water perching effects. So, further investigation of the effects of water perching, the research conducted dynamic simulation using framework model of the rock. The model assumed a constant porosity, permeability could be adjusted in different simulations according to the table number 1 as written on the slide. The model had a high resolution of 5 meters in the vertical direction, allowing detailed analysis of different in free water level within range 10 to 100 meters. The 3D model used in the study uniform throughout with consistent porosity, which affect permeability. Zone number 2 is separated from zone number 1 and 3 by lateral barrier and allows fluid exchange at the top. Each zone is monitored by vertical well. During the simulation, parameters such as saturation, pressure, and relative permeability are observed along this well. A cross-section of the model at the end of simulation show the final saturation, including example of perching corresponding to the free water level. The model used in the study, I think, 1,000 again, 1,000 and 1,000 meters XYZ direction to create a trapping condition in the central part of the model. Zone number 2 is separated laterally, 2 barriers. At the bottom is sealed to prevent fluid flow. Zone 1 and 3 are connected, while the injection occur at the top of where all 3 zones communicate laterally. Sorry, I'll go back. The oil-water interaction describe it, The next slide, the oil-water rock interaction is described with one of the famous equation, Brooks-Corey saturation height function, which was proposed by the research in 2012, I think Julia and Nichols, while this function characterized the relationship between the saturation of water and oil in the rock at the capillary pressure. It helped in understanding how fluid move distributed within porous rock formation, which is important for studying phenomena like water perching, predicting the behavior of reservoir. The entry pressure, PCE, and capillary pressure shape factor, NPC, both two parameters are varied in simulation. The entry pressure represents the pressure required for fluid to enter the rock, while the capillary pressure shape factors influence the relationship between capillary pressure and fluid saturation. Throughout the study, the water saturation at infinite mean that capillary pressure initial is kept constant at 0. In the second equation, relative permeability curve are used to describe the flow behavior of water and oil in the rock. These curves are parameterized in similar way, meaning they have a comparable shape for both water and oil. This allows researchers to analyze and understand how water and oil move through the rock formation under different conditions. The parameterization involves fixing the water content saturation SWC at 0.2, which ensure the water remains immobile at specific capillary pressure for certain value of the Corey parameter. And this condition is necessary to, I think, accurately model behavior of water and oil in the rock formation being studied. The next following figures explain and provide an example of relative permeability capillary pressure curve used in simulation. The relative permeability curve represents the relationship between the flow of water, the flow of other fluid in porous medium, while the capillary pressure curve describes the pressure different across the fluid interface. The figures demonstrate how different parameters such as the water Corey exponent, capillary pressure shape factors affect the behavior of the curve and their impact on simulation outcome. The relative permeability curve used in simulation will represent the relationship between flow of water and the flow of other fluid in porous medium. The Corey exponent defined by equation number 2 varies from less than 1 to greater than 5, covering a wide range while keeping the constant number at 2. Sensitivity analysis conducted for number of value 2 and 5, and showing they didn't affect the outcome of simulation. While the figure B describe the relationship between water saturation and depth is shown by coupling the entry pressure permeability using two different capillary pressure shape factor values. The effect of NPC can be observed within same colors, while comparison of colors reveal the impact of entry pressure. This kind of information help in understanding how different factors influence the water saturation different in relation to the depth. Saturation height model and relative permeability function as depicted in these figures are incorporated in the model presented in the previous slide, where these functions are utilized independently, varied parameters as specified in the table number 1 to analyze their impact on simulation outcome. The simulation results, as we can see on the slide, depict variation in the free water level different ranging from 10 to 100 meters. The left side of the figure shows saturation versus depth profile, while the right side display a pressure plot that determine the free water level. The simulation assume constant oil to water density, difference 0.45 gram per cc, and surface tension IFT 26 dyne per centimeters. As the result of significant number of simulation, I think it's around 20,000 iterations that were conducted to understand the phenomenon of perching. Simulation focused on the difference in the free water level between zone 2 perch and zone 3, which serve as diagnostic indicator for perching. Simulation identifies several factors that are sensitive to perching, including free water level in zone 2, free water level in zone 1 and 3, the elevation difference between the free water level, barrier height, entry pressure, rock permeability, and capillary pressure shape factors. In the simulation, various input were tested based on the table number 1. The resulting impact on the free water level was observed. The findings show that only a minority of simulation resulted in perching, with the capillary pressure shape factors and entry pressure having the most significant influence. As the rock permeability decreased, the occurrence of perching decreased, and it observed that perching cases are more common in low NPC, low capillary pressure shape factors, and low entry pressure, which correspond to the high permeability. So the following given figures kind of illustration number of key factors control phenomenon called perchings in the data set. Perching is influenced by two factors. We name it the capillary pressure shape factors and entry pressure. The figures also show the distribution of values for these factors, with blue corresponding all input values, and the orange the specific values that leads to perchings. Additionally, a cross plot PCE versus NPC demonstrate the combined values that result in perchings. One of the interesting observation is that in order for perching to occur, there is an inverse relationship between the capillary pressure shape factors and entry pressure. As the capillary pressure shape factor increase, the entry pressure should be decreased. Otherwise, the perching's effect disappear. And this relationship, as illustrated in the figures, I think in figures number C. The observation state when the free water level in the perch zone is deeper, indicating higher entry pressure, the ratio of cases where perching occur decrease compared to the total number of cases. As the entry height increase, the interval of height required to trap the water increase, allowing for more hydrocarbon to be accommodated in the trap zone. Therefore, for a given volume of injected hydrocarbon, the chance of perchings happening decrease as the free water level in the traps become deeper. This relationship is illustrated, I think, 7A, where the position of the free water level relative to the barrier is compared for all simulation. It observed that when the free water level 2 is closer to the barrier than 400 meters, it's correlated with perching. Okay, which refer to the trapping of water in specific zone. This correlation is specific injected volume used in the simulation, while 7B cross plot comparison the free water level in zone 2 versus the free water level in zone 1. The plot show wide range of values, but perching, which is a specific phenomenon observed only for the orange dot that deviate from one to one line. This suggests that there is relationship between the free water level in different zone and the occurrence of perching within certain condition leading to this phenomenon. The provided example, the next figures 8 illustrate the occurrence of perching. Water perching is influenced by relative permeability, which means that the ability of water to escape at the point which it become immobile are determined by the relative permeability values. Understanding the relationship between relative permeability and water perching is crucial in analyzing, predicting fluid behavior in reservoir. As we see, the figures show the water saturation plot against depth for both perched zones orange and the normal zones blue. At the end of simulations, it's also displayed the relative permeability of water and oil plot against depth for wells number 1 and 2. This information help understand the relationship between water saturation, relative permeability, and also distribution of zone within the reservoir. In the series figures 9, the saturation profile at the end of simulation are compared for different cases based on the height of the transition zone. The reference point for well number 2 NTVD subsea is adjusted according to derive different in free water level between zone 1 and 2. And the minimum saturation is observed is determined by the minimum mobile water saturation as influenced by the relative permeability curve. Interestingly, no difference in saturation is observed between the transition zone at the same height above the free water level. So now we look at series of equation. Equation number 3 to ensure the perching is not limited by migrating hydrocarbon and through formation thickness, relatively high amounts of hydrocarbon are injected in subset of simulation. The entry pressure, which indicate rock quality, is linked to the permeability using the equation that involve oil-water interfacial tension, permeability, porosity, and contact angle. While the equation number 4, another important finding of the study is the enhanced comprehension of capillary and buoyancy force in the reservoir. Capillary pressure, which is the pressure difference between two phases, can be determined by extrapolating the gradient of water and hydrocarbon. However, in the case of perched contact, there is an apparent inconsistency in calculating capillary pressure. The capillary pressure at the top of reservoir should be consistent regardless of whether there is a perched contact or not, as opposed to the approach suggested by Adams in 2016. This means that the pressure difference between two phases should be the same, regardless of the underlying condition. Additionally, buoyancy refer to the density difference between water and hydrocarbon, affecting the pressure different distribution in the reservoir. So the next equation number 5, the concept of capillary pressure, its relationship with the equilibrium of the system. It states that despite the assumption capillary pressure would be different between wells with depth and perched contact, this would lead to different pressure and cross flow, which is not observed. It's also mentioned the role of buoyancy suggested that discontinuity in capillary pressure could be expected between the free water level and their barrier edge. So moving through the next slide, The influence of rock permeability on the elevation difference between the free water level and the barrier in perched zone. When the rock permeability decrease and the entry pressure increase, allowing the free water level to penetrate deeper into the perched water zone before becoming immobile at the barrier edge. The plot data, as we can see in the figure 10, represent instance where perching occurs, indicating that free water level in zone 2 is higher in zone number 1. The following figures trying to illustrate the change in saturation over time for different permeability values in a simulation, where the left side represents a case of permeability 100 millidarcy that leads to perching, while the right side represents a case with a permeability lower up to 1 millidarcy that doesn't lead anything to perching given sufficient equilibrium time. The figures show final saturation at the end of simulation with the poor rock lagging behind initially, but eventually allowing water to escape while a good rock maintained a consistent water level. So in the context of simulation, as we can see, cross plot figure C through F, E, D, C, C, D, E, and F refer to the final saturation at the end of simulation process. These figures illustrate the distribution of oil and water in reservoir after the simulation has been completed, and the different saturations are A to D as an initial state of injection process in reservoir with varying rock qualities suggests that at an intermediate step, the poor rock lags in terms of water movement compared to the better quality rock. However, given enough time, the water will eventually escape from the poor rock, contrasting with the behavior of the better quality rock represented by the different colors with red, magenta, indicating high oil saturation, cyan representing 100% water saturation. At intermediate state B, in the presence of poor quality rock, the water lag in the central zone compared to the good quality rock. However, given sufficient time, the water will eventually escape from the poor rock, in contrast to be the good quality rock where the water remains immobile. And this observation suggests that the permeability and the quality of rock play a significant role in determining the movement escape of water in the subsurface. The next figures, number 12, show porosity permeability data represented by different color based on the Perched discriminators, while B illustrate the relationship between number of observed perching cases and permeability, indicating that a lower permeability corresponds to the lower likelihood of perchings occurring. And this is suggests that there is a connection between rock permeability, the occurrence of perching with lower permeability, reducing chance of perchings. Figures number 13, I believe, illustrate water saturation and formation pressure for the two wells. One position in perched zone, well number 2, orange color, and another penetrating in normal zone, well number 1, zone sound in the blue line. Based on the assumption oil phase buoyancy equilibrium with the capillary pressure, there is discontinuity in capillary pressure between these two wells, actually, indicating a lateral variation. By calculating the capillary pressure along the well trajectories are different in capillary pressure at the top of reservoir between well 1 and well 2. It also suggests that rock quality difference may influence the behavior of perch contact in subsurface model. The next slide, as we can see, the figures represent the monitoring of fluid properties along the well. Well 1 is a regular aquifer. Well 2 is situated a region prone to the perchings. The figures display water saturation, phase pressure, capillary pressure, fluid gradient, and also water relative permeability. The equation PC is defined equal pressure difference oil minus pressure difference of water, represent the calculation of capillary pressure by subtracting the pressure of the oil phase from the pressure of the water phase. The monitoring of fluid properties in these two wells, as we can see, well 1 goes through a normal aquifer. Well 2 is located in zone prone perchings. The fluid properties being monitored include SW, phase pressure, capillary pressure, fluid gradient, KRW. Another figure show saturation versus depth for perching case, highlighting the development of capillary pressure along the stool, with maximum pressure between them, discontinuity only within the barrier. Calculated buoyancy is also plotted, and a difference between capillary pressure. Calculated buoyancy is emphasized, revealing a significant discrepancy at the reservoir top. So again, these figures, graph A shows the variation of water saturation along the depth in perching case with the development of capillary pressure, while B along these two wells, the capillary pressure reaches its maximum between two wells, and discontinuity is observed only within the barrier. The graph also includes the calculated buoyancy plots along the same trajectory. By comparing the capillary pressure difference with the calculated buoyancy, a significant discrepancy is identified at the top of reservoir. So I think this is my last slide. The takeaway message, all of explained earlier as lesson learned. First, I think capillary pressure and buoyancy are often assumed to be in equilibrium, but there is a confusion between these two concepts. When buoyancy increases, more water is forced out the rock until it's become immobile. Above the certain depth, capillary pressure and buoyancy is no longer appear to be equal, because of buoyancy assume the pace exerting the Archimedes force should be mobile. Therefore, when water becomes immobile, the concept of buoyancy becomes redundant, and the maximum capillary pressure concept should be used when dealing with the perching. The second takeaway, when we obtain result show a significant implication addressing the connectivity of hydrocarbon volume, in particular relation to optimizing well spacing. By identifying, understanding perch contact and their control mechanism, we can preserve hydrocarbon connectivity and potentially extract valuable information about barrier height based on the rock properties. The transition zone signature offer a potential approach to reduce hydrocarbon volume and predict water production by avoiding well drilling, especially in low permeability areas of the field. The last things is perching contacts in reservoir can lead to confusion, variability in the free water level and hydrocarbon distribution, while few perching case involve no hydrocarbon below the free water level, and hydroactive aquifer can be associated with both free water level different as residual hydrocarbon. More complex reservoir history, tilting the reservoir can result in appearance of hydrocarbon below the free water level. This study focused on homogeneous model, while the heterogeneous model hysteresis effect are subject other research, I believe, suggested for the next opportunities when considering factors beyond the primary drainage. I think that's all my short talk on the topic of the perched water level, perched oil water contact concepts. Hope everyone can enjoy it. Thank you all for the listening and see you next time. Wassalamualaikum warahmatullahi wabarakatuh.